Hi, welcome to this podcast, which is about the shape of the sine function. So, what I want you to think about is over here we have I pay no attention to the right side here, but over here on the left, you can see that we have a unit circle, and you can see that I can drag the terminal ray to all the different locations in the unit circle. So, what I want you to do is take a look at this triangle, and you can see these measures here. What they're doing is they're looking at the angle, right? And then it's telling you how long the opposite side and the hypotenuse are. We're going to call these U and R. And then it's looking at the ratio of those two, right? So here, since it's on the unit circle, the radius, the hypotenuse is always 1. And you can see that as I go around the unit circle, the um, the opposite leg gets longer and longer and longer until it's almost the same length as the hypotenuse. And then at 90 degrees, it's going to be actually the same length as the hypotenuse. Okay, so what we're doing is we're thinking about this as a function, right? Thinking about what is sine of theta as a function of theta. You can see here, right, theta gets bigger, so does sine of theta, right? And what's happening over here on the right is it's actually tracing out what's changing with sine as the angle changes. So this axis here, right, is the angle, and then the y-axis here is the ratio of sine, right? So this is a graph of y equals sine theta. So let's go back, and we're going to start here at 0, right? We can see that at an angle of 0, sine is equal to 0, and then as I get to an angle of uh, 30 or so, right, we know that sine is going to be 1/2 from what we know at our unit circle, and that's exactly what we see here and here. And then it's going to keep getting bigger until at 90 degrees, sine is equal to 1, right? And then as we go down past 90 degrees, we can see that sine is getting smaller and smaller and smaller and smaller and smaller again until I get to an angle of 180. Oops, went too far. When it is at 0. Right? And then it's going to get negative until it's at 270, and then it's going to be at -1, and then it's going to go back to 0. And you can see now that what we have going on here is that this is the shape of the sine function. What's going to happen for angles past 360 degrees? Well, it's just going to repeat itself, and you can kind of see this in because on the unit circle r is always equal to 1, the v coordinate is always the same thing as the sine value. And if you look at this, it's kind of cool that the height, the v, right above the x-axis is always corresponding to the height of the sine graph. Let me show you what I'm talking about. I'm just going to be a little silly here. If I connect these 2 points, right? Oops, let's not have that second selected. Let me try again. Okay, if I connect those 2 points, we can see that as I go through all the different angles, those are always at the same height. In other words, that line is always horizontal. So that's kind of cool. And we can see that this is the shape of the sine function. If I go and look and see how cosine is different, right? I have an angle of, it's going to be the angle here, and if I look at how long the legs are and the cosine value, we can see that here cosine starts out with cosine equal to 1, and then it goes down to 0, and then at 90 degrees it goes negative, right? And then it's at -1, and then it goes back to 0, and then it goes positive again for the last quadrant. You can see, though, that ultimately, as we do this, the shape of the cosine graph is exactly the same as the shape of the sine graph, except for it starts at a different place in the cycle, right? So cosine starts here at theta equals 0 at the peak of the graph, whereas if I go back and I look at sine starts at 0, or sine ratio of 0 at an angle of 0. If I go and I look at tangent is even, it's a very different thing, right? So the legs here are opposite over adjacent, the tangent value, right? You can see here for a small value of theta, right? The opposite leg is very small compared to the adjacent leg, and the tangent is very close to 0. Now it's going to get bigger, bigger, bigger. Now at 45 degrees here, I'm going to try to get close to it. you can see that the opposite and the adjacent sides would be the same at 45 degrees and tangent would be equal to 1. As I get even bigger to an angle of 90 degrees, right, I see that what's happening here. Oh, I'm going to try to inch up here, right? So like tangent is very large, 88 degrees. And then as I get even closer, even bigger, 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 tangent is very big at 89.63. And then if I go, whoa, at between 89 and 90, tangent switches from being very large and positive to being very large and negative. So there's a discontinuity in the tangent graph here, which is kind of weird. Let's look at what's going on here. Right, this is just going to show the point here in my graph, right? It starts here at 0, right? It goes big, 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 without bound, and then it comes up from the negative section over here. That's weird, right? Going again, looking at it this time where it's leaving a trail behind of what's doing, right? There's tangent. Bigger, 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 bigger. Whoa! And then it starts from down below. It comes back up. Oh, there it is. And then you can see in the third quadrant, the tangent ratio becomes positive again, and we see that same pattern repeat itself. So tangent has a fundamentally different shape than that of sine and cosine. Now, but crazier and more fun. Now the sine and cosine graphs, that shape of the graph, those are called sinusoids, right? So this shape that we have here, where it's got this wavy motion, that's called a sinusoid. Even if it's not a sine graph, if it's a cosine graph, sine and cosine graphs, the family of those are referred to as sinusoids. Okay, and that is all there is to it for the parent functions of sine, cosine, and tangent.